All right, so today we're going to be talking about heat energy. Don't forget to take notes on the red slides. You should have the notes handouts to go with this. And don't forget to look for the owl and summarize what you learned at the end. So what exactly is heat anyway? I mean, what is the difference between this cold water over here and this hot water over here? What physically is the difference? I know the temperature is a difference, but that's just a measurement of heat. I want to know what is actually physically different about these two things. So I want you to take a look at the animation on this next slide and write down what it says, since it's a red slide after all. And this will explain a bit to you, and then I'll be right back. Okay, so heat is really just a measurement of how fast the atoms of something are moving. And as we've said before, everything is made of atoms, and these are really small, too small to see, but everything is made of atoms, and heat is a measurement of how fast these atoms are moving. Now, I want you to look at these pictures here, and I want you to think, are these atoms moving even in ice cubes and bricks and rocks and mountains and things like that? Well, the truth is that these atoms actually are moving. If you could see the atoms inside of them, they would look kind of something like this. They stay more or less in place, but they're kind of jiggling around all the time. And so as you heat something up, that jiggling starts to get faster and faster. And when something melts and becomes a liquid, that just allows those atoms to kind of move around a little bit more freely. And so they're still moving, and now they would be moving faster than when they were solid. But even when they're a solid, they're still moving around. So if that's true, if heat is then just how fast atoms are moving, well, what would we have to do to something in order to get the atoms to come to a complete stop? Well, if heating something up makes atoms move faster, then it makes sense that cooling something down would make the atoms go slower. And in order to get them to completely stop, well, you would have to remove all of the heat energy from them, and they would have to have zero energy. And this idea is what we call absolute zero. It is absolutely really zero. And this is something that is measured on the Kelvin scale. So this is 0 degrees Kelvin. And notice that this is the theoretical point at which all energy is removed from the substance. And the reason why the word theoretical is in there is because this is not something, as far as we know, this is not something that actually exists in the universe. We've never really seen something that's at absolute zero. And as far as we know, as far as we can figure out, even though we've never seen this, we think that some pretty weird things happen when you get to absolute zero. Like objects can kind of move right through other objects and things like that. It gets to be pretty strange. But like I said, this is not something that we think actually exists in the universe. It's just kind of like an idea. And so this is 0 degrees Kelvin on the Kelvin scale. So you can see several different temperature scales here. And 2 of these 3 scales are scales that we would use in science class. The third one is something we would not use in science class. But I want you to fill in all of the missing numbers here, and I want you to kind of notice some things. First of all, if we look at the Celsius scale to start off with, the Celsius scale is probably the one that's most commonly used around the world and the one that's most commonly used in science class. And you can see some very important points on here. First of all, the freezing point of water, the point at which water freezes, is 0 degrees Celsius, and the point at which water boils is 100 degrees Celsius. So this is actually how the Celsius scale was made. They said, let's make the freezing point of water 0, let's make the boiling point of water 100 degrees, and then we'll try and kind of make everything in between the in-between temperatures. Notice that this is 212 degrees Fahrenheit and 32 degrees Fahrenheit. You may already know that 32 degrees Fahrenheit is freezing temperature. And also notice that the freezing point of water is 273 degrees Kelvin. What that means is that 0 Kelvin is a really, really cold temperature, even compared to the temperature of ice. This is 273 degrees colder than ice. So this is really, really cold. This is cold beyond anything that we are familiar with in our everyday experience. This is a cold that really never happens, especially on Earth, and really rarely happens. We rarely even get close to this in anywhere in the universe. So, make sure you know some of these temperatures, okay? We need to know what absolute zero is. We need to know that Celsius is 100 degrees is the point at which water boils. 0 degrees is the point at which water freezes. As far as I'm concerned, the Kelvin scale is really the only one that makes sense. If you're in a car and the car speedometer says 0 miles an hour, that really should be the point where the car is not moving at all. Well, just similar to that, absolute zero is the point at which atoms are not moving. So it makes sense to call that 0 because the atoms are actually not moving at that point. Okay, so we've talked about heat, and thermometers are what we use to measure heat, but how does a thermometer work exactly? Well, I want you to think of it like this. When we add energy to something, when we make something hotter, it's kind of like playing pool. It's kind of like that white cue ball running into all of those other balls that you see here. And when you do that, you add energy to it and you get those other balls, or what would really be atoms in a real substance, you get them moving around faster. And something you notice is that when you add energy, all of these guys kind of tend to spread out. They get further apart from each other and they take up more space, right? They start off just taking up the space of this little triangle right here. And then once the energy is added to them, they take up so much more space all around here, all over the table. They take up all of this space now. So what we could say is that when we add energy to something, when we add heat energy to something, the atoms move faster, they start to bump into each other harder, and they spread out more, taking up more room. So in a thermometer, you have this liquid. And when you put the liquid in something hot, the same thing happens that happened to the billiard balls in the last slide that we saw there. They start to heat up and they start to move around faster and they start to bump into each other harder. And so they start to take up more space. And so the liquid actually gets bigger. It expands. It takes up more room in the thermometer. So this process is what we call thermal expansion. We'll talk about hot air balloons and how this works, but this is basically the idea of how hot air balloons rise. The air in the inside of the balloon gets heated up, it expands, and so it becomes less dense than the air surrounding it, and it floats. Okay, heat and temperature. These are terms that we usually use kind of interchangeably in normal everyday life, but are they really the same thing? Well, I want you to take a look at this picture here. So what's the difference between these? Well, they definitely have the same temperature. You can see this line here and this line here. Both of the thermometers are at exactly the same temperature. So they have the same temperature, but there's a different amount of water in this one than there is in this one. This one has less water, this one has more water. And so because of that, there is a different amount of heat energy in this one than there is in this one. They're at the same temperature, but the overall amount of energy in the larger container has more atoms, and therefore it has more heat energy. So we can say that temperature is the average speed of the molecules in a substance. And notice that word average there. You're kind of taking the speed of all of the atoms and getting an average. You're getting a sense of how fast is the average atom going in this container. But heat is the total amount of heat energy in a substance. So in this situation, we're actually adding up how much energy each individual atom has. We don't actually have to add them up one by one. We can do it in other ways, but the idea here is that's basically what we're doing. So if each one of these guys has, let's say, 10 degrees of heat energy, then the temperature is the same. It's 10 degrees for both containers, but because the larger container has more atoms, we have to add all those tens together. And because there's more tens over here, we get more heat energy over here than we do in the smaller container. So temperature is kind of an average. It's getting a sense of what speed each of the atoms are going at. Heat is really a total measurement of how much energy is in that. So the more stuff, the more heat energy it has. So in your notes, I want you to try answering this question. Which one of these pictures has a higher temperature? That should be fairly obvious, right? And which one has more heat energy? Remember, now this is in the ocean over on the left, and this is just a glass of water over here. So remember, heat energy depends on how much actual stuff there is. So think about that and answer that in your notes. I'll be checking that in class. Okay, so the next thing we have to talk about is the transfer of heat. In other words, heat moving from one place to another. And you can see some different ideas of this. So we have like a metal rod here, and it's being held over a fire, but you guys know that even though the fire is not touching this end of the handle over here where the glove is, that part will still get hot because the heat kind of moves from one end to the other. We also have this idea of heat rising. You might have heard of this idea of heat rising before. So if you put your hands over the top of the flame, it gets really hot. And then we have this idea of heat kind of moving in waves here. Okay, so let's talk about these three ideas. First, we have convection. Convection is the simple idea that hot things rise and cold things sink. So what you get is sort of a circular movement where cold things sink and hot things rise. Cold things sink and hot things rise. That is convection. Another way that heat can move through an object is through conduction. Now this is heat moving from one molecule to another. We're heating up the atoms or the molecules right here, and they start jiggling around a bit, and they bump into the atoms next to them and they start jiggling around a bit, and then they bump into the atoms next to them and they start moving around a little bit, and they bump into the atoms next to them and they start moving around a little bit. And that happens all the way down the line until you get to this point where the atoms right here start bumping into the atoms in your hand, and the atoms in your hand start jiggling a little faster, and then you start to feel that heat. And you're familiar with this idea because you've seen this kind of thing before. You understand that even though that the oven is only kind of touching this part, the bottom of the pan here, that heat will actually move through the pan and get this part hot here. So you can't touch the handle either, even though this part is not actually touching the stove. So same thing as before. These atoms start jiggling really fast and they bump into atoms over here, which start jiggling really fast, which bump into atoms over here, which start jiggling really fast. And last but not least, we have radiation, which is heat moving in waves. Radiation. One of the main examples of this is the heat that comes from the sun to the earth. It's kind of an interesting thing because we're talking about heat as the idea of atoms moving fast, but this heat actually travels through empty space. So in this case, it's kind of an interesting question to ask, what is actually jiggling here? If there's no atoms in empty space, then what's actually moving back and forth? It's a little hard to explain. We'll talk about this in class, but the answer, surprisingly enough, is that it is space itself that is vibrating. And so that's what brings the heat from the sun down to the earth, and that's radiation, heat moving in waves. All right, so there you have it, ladies and gentlemen. We have the kinetic molecular theory, which basically tells us what heat is, which is the speed of atoms. The hotter something is, the faster the atoms move. That brings us to the idea that if you actually get the atoms to stop by taking away all the heat energy, that is what we call absolute zero. We have a couple different temperature scales that we learned about. Celsius, remember 0 is the freezing point of water, 100 degrees is the boiling point of water. Kelvin, the only temperature scale that actually makes sense because 0 is the point when atoms are stopped moving. We have the idea of thermal expansion. As atoms heat up, they start bumping into each other harder and they spread apart. We have different types of heat transfer. We have convection, hot stuff rises, cool stuff sinks. We have conduction, atoms sort of bumping into each other and heat moving through a substance in that way. And we have radiation, the way that heat gets to us from the sun by waves.